Hello, everybody, and welcome back. Today we are going to continue our conversation about oceans. We are on Unit 5, Lesson number 2, and as always, you should have downloaded your interactive notebook pages for the day. These notes go along with those pages. So today we're going to talk about something that's actually a little bit of a review. We're going to talk about something called differential heating. Now, if we think back to a couple of units ago, we started talking about this idea of differential heating and how different items will heat up at different rates. So typically we're going to see that land heats up faster than water, and that's going to impact our coastal climates and also our inland climates as well. So we're going to take a look at that today. So just to review on what the hydrosphere is, remember we learned about this in one of our very first lessons when we talked about the branches of earth science. But the hydrosphere is just all of the water on the earth, right? So the water on and in Earth's crust make up our hydrosphere. Hydro meaning water, and then sphere is just in relation to the earth. So 97% of the water on Earth is contained in the oceans. So that means most of the water on Earth is ocean water. Now, the other 3% is fresh water. And fresh water is what we learned about in our last unit. So that fresh water, is in lakes, rivers, streams, and also groundwater and glaciers as well. So the physical properties of seawater. Seawater is salty, so that means there are salt ions in the water, and this makes the water more dense, so it's heavier. So the saltier the water is, the heavier it will be, and it will sink towards the bottom. Remember, that's what contributes to the movement of those currents in the ocean. So temperature will affect density as well. So the colder the water gets, the closer the molecules get to each other, creating a higher density, which makes it heavier. So cold water is more dense than warm water, just like air. So when we talk about the movement of these convection currents in our ocean, it happens just like in the mantle, and also we'll see it happens in our atmosphere as well when we get there. But basically, this water, it will move in these currents. So towards the equator, when it's near the equator, there's a lot more radiation from the sun, and so the water heats up and it rises, and it will move through the currents towards the poles. Where at the poles, there's not as much heat, right? There's not as much radiation from the sun, so the water cools down. And as it gets colder, it becomes heavier, more dense, so it sinks down. And then it will move towards the equator, and the process will happen again. That's what creates this conveyor belt-like movement of those currents in the ocean. So the ocean is layered, so temperatures in the ocean will range from -2 degrees Celsius in the poles to about 30 degrees Celsius in equatorial regions. The temperatures tend to decrease with depth, which makes sense because closer to the surface you have more sunlight penetrating and therefore more radiation, which heats the water. So deep ocean water, even in the tropics, is always cold. So even near the equator, if you go down deep enough, the water is going to be cold. And then the layering is caused by temperature differences. So cold water is more dense, it sinks to the bottom, and then the warm is less dense, so it rises to the top. And that's a concept that we've talked about quite a few times now. So remember, the heating is caused by the radiation from the sun. So there's more radiation on the equator beating down, which means it's going to warm up the temperatures, the surface waters there, more than it will in the poles. So the difference in the density along with the rotation of the Earth moves currents away from the equator and toward the poles. Why is this? Because the sun shines on the equator all year long. So the equator is the middle part of the Earth, right? It's that kind of imaginary line that goes around the center of the Earth. And it's kind of just always constantly pointed towards the sun. So we know that the seasons are caused by the tilt of the axis, but when you're in the middle of the planet itself, you just get constant sunlight all year round. So the heat from the sun is input to the ocean. The warm water will eventually move with the currents towards the poles. As it gets to the poles, it loses heat and it will sink and start to mix because it's cold. And remember, cold water is more dense. Then it will make its way back to the poles, and as it gets here, it will warm up again, and the process will repeat. As a reminder, this is called a convection current, just like the ones that are in the mantle that move our plate tectonics. So specific heat is a concept we need to talk about, and when we refer to the specific heat of a substance, that's just the ability of the substance to absorb or release heat energy. So if a substance has a high specific heat, that means it takes more energy to raise the temperature. So you'd have to get, in terms when we're talking about sunlight hitting the earth, there'd have to be more sunlight and more radiation to raise the temperature. So water, specifically the ocean that we're talking about here, has a higher specific heat than land. So what does that mean? It means that it's going to take a lot more energy from the sun to raise the temperature of the ocean than it will to raise the temperature of the land. And that goes back to that concept of differential heating. So differential heating, again, we've talked about this before, but it's always good to review. So remember, differential heating is just the idea that different substances require different energy to heat up. So land will absorb and release heat quickly. So solid, the molecules are closer together. So the sunlight is absorbed by the surface only. So here the sunlight cannot penetrate into the ground because it's opaque. So all of this radiation will be absorbed and the land will heat quickly. Water, on the other hand, will absorb and release heat slowly. So the liquid molecules are further apart, and the sunlight can be absorbed up to 200 meters deep. So the sunlight will penetrate the water, and it will get kind of dispersed throughout here, so it will take a longer time for that radiation to be absorbed and to heat up the ocean. So the high specific heat is actually the property that allows water to retain the energy needed to power hurricanes, because that energy stays in the ocean a lot longer than it stays on land. So when we're thinking about going to the beach on a hot summer day, when the sunlight is beating down onto the sand will heat up first. So if you run out at noon on a beach and the sand is super hot and it's burning your feet, you can run to the ocean and the ocean water will be cool because that sand has heated up a lot faster than the ocean. However, if you go back at the end of the day, like when the sun is setting, if you want to look at a sunset on the beach, that sand will have cooled off because the land heats and cools quickly. But when you make it to the ocean will feel warmer in the evening because it's had all day to heat up and now it's slowly releasing its heat. So it took all day to heat up and it's probably going to take all night to release that heat as well. So this is important because it leads to something called land and sea breezes. Now, if you are watching this, you can go into the slides and play this video. I'm not going to play it right now because we'll watch it in our Zoom meeting. But if you missed the Zoom meeting and you are watching this or reviewing, I highly recommend going back into the slides and playing this because it explains the land and the sea breezes perfectly. But basically what happens is that during the day, the land heats up a lot faster than the ocean does. So as the land heats, the air above it will warm up and it will rise into the atmosphere and it will be pushed this way because it creates an area of lower pressure. And then here we've got the cool air above our ocean that is being pushed to the land. So it's a convection current the same way we see in the oceans as well as in our mantle. So the warm air rises, it's pushed this way because there's an area of high pressure from the ocean and then a low pressure in the atmosphere. So the warm air will be pushed to the sea and then the cool air that's above the sea will be pushed to the land. This is called a sea breeze. So the sea breeze will bring the cool air and blow it towards the land during the day. Now at night, when the sun starts to go down, we see the opposite happened. So since the land cools off quicker, the cool air is now above the land and the warm air is now above the ocean because the ocean is warmer at night. So now that air that's above the ocean is going to rise and then the cool air that's on the land is going to be pushed towards the sea. So during the day, you would be getting a cool breeze towards the land. And then at night, your cool breeze is going to blow towards the sea. So during the day, if you were to be facing the ocean, you would feel the cool breeze on your face. And then at night, if you were still facing the ocean, you would feel the breeze on your back. So just to recap, the breezes are named for the areas in which they originate. So a sea breeze moves from the sea to the land. So the cool air is moving from sea to land, and that's during the day. And then at night, a land breeze moves from the land to the sea. So the cool air is moving from above the land to the sea. So during the day, you have your sea breezes, and then at night, you have your land breezes. So these currents and these differential heating will affect our coastal climates. So coastal climates like Myrtle Beach in South Carolina are affected by the changing temperature of the ocean. So during the day, the sea breeze will push cool air to the shore, and then at night, the land breeze will push cool air to the sea, and this will regulate the temperature of coastal areas. So it will cool the shore during the day. If you guys have ever been to the beach, it's actually cooler on the shoreline than it is if you were to go off of the beach. And then also at night, the beach is going to be a little bit warmer because that cool air is blowing from the land out towards the sea. So it does regulate the temperature in coastal areas. However, inland areas such as Charlotte are surrounded by more land, so the ocean has no effect on the overall climate. So our Atlantic Ocean that borders the North Carolina coast does not really affect our temperatures here in Charlotte. So our temperatures instead are regulated by the rising and the setting of the sun. It's warmer during the day and then cooler at night. And then here it's just kind of a temperature breakdown of the state. So we see here in these coastal areas, so if we take a look at these temperatures, these are cooler and then we get warmer. So we've got, of course, our coldest here in the mountains because we're at higher elevations. And then as we move, it gets a little bit warmer towards the coast as well. But these coastal areas are regulated by the temperatures of the ocean. So that differential heating on the ocean and those sea and land breezes. So that's it for this lesson. If you guys have any questions, let me know. And if not, I will see you guys in the next one.